Okay, so here's the idea. I'm going to draw it here on the board in a minute, but I'm going to do it as an animation first. This right now is just a curve in the x-axis. Okay, if we were to rotate this around the x-axis, right? If we were to take this and rotate this around the x-axis, one thing we could do is take that same idea of that little infinitesimally small rectangle and just wrap it around, where the hell's my rotation? There we go. Wrap just that rectangle around the x-axis. If I wrap just that around the x-axis, then I create a cylinder, right? In this particular case, it's a cylinder. And I have a formula for the volume of a cylinder, don't I? So if I can somehow come up with a general formula that would give me the volume of each arbitrary cylinder, then the integral will add that up, right? It's just like, instead of doing, you know how the integral originally was f of x times d of x? It was f of x dx like that. And I was really trying to I've been trying to beat into you that that's the height of the rectangle, that's the width of the rectangle. It's just a formula for area, right? And then we're adding them all up. If I can come up with a formula in here that gives me the volume of that cylinder, then the integral will add them up. And I can just use the integral to get the volume. So the more, as I slide this rectangle around, it changes the shape of the cylinder, right? The cylinder changes shape. So my formula needs to account for that movement. What else? If I do a bunch of them, right, the more of these I do, it's kind of like the idea of the Riemann sums. The more rectangles you do, the closer and closer you get to the true solid shape, right? That's, I don't know how many rectangles, that's a lot of rectangles in there, okay? And that's the true one. It's hard to see the two. So that, whoa, the heck is that? Oh, number of cylinders. There we go. So, looks kind of like a football. You get the idea? Yeah? Okay. So, let's go try and develop a formula, all right? Because really that's all we need. We need a generic formula to wrap any region around the x-axis. So here we go. Let's say we have a function on top. Let's call it f. Let me use some colors here. Say we have a function on top. Let's call that f. Let's do a function on the bottom. Call this one g. And then they hit each other, or we're going to start and stop here at A and at B. We have our axis of rotation here. I'm going to symbolize that with two little curved arrows like that. And now my task is to see if I can come up with a formula to represent one single rectangle in here being wrapped around. So I'm going to draw a rectangle. And it's going to be arbitrary, right? It's going to be just somewhere in here. And then I have to imagine what that would look like wrapped around. So my advice to you is that you don't try and draw it right there. I recommend you come over here on the side and you draw your x-axis, draw your axis of rotation, which happens to be the x-axis again, right? The x-axis and the axis of rotation are exactly the same. And then I would draw your rectangle here, like that. And then think about what that would look like if you wrapped it around there. What would it look like? Would it be a cylinder, a box, a cylinder, a shell, not a shell, a washer? What would it be? It'd be a washer. It would look like a washer, just turned this way, right? So let's maybe you can try to draw it over here. It would be, how big would it be? I don't know, somewhere about this big. I don't know. Yeah. It doesn't have to be perfect. Right? That's what it would look like, kind of. But it's hollow on the inside, isn't it? Like this. That part's not as important. That's just so you can see. That's what would happen if I wrap this thing around the x-axis, right? If I wrap it around, that's what I would get. To find the volume of this, I need to know, go back and think about the formula. It was what do we need? For the washer. We needed R out, R in. We needed the height. And that was it, right?
No, they need to be squared, right?
Pardon me?
They need to be squared, right? Pi r squared.
Pi r squared, yeah, but it was, well, let me just bring it. Yeah, I'm gonna bring it up. Nope.
H times I times R times open parentheses R out minus R in.
It was this one, right there. And I had written it in a certain way, and y'all were like, why did you write it that way? You don't like it that way?
I like it that
Oh, okay, yeah. So I'm going to use that formula right there, okay? Yes?
So we have to square each individual R?
Each individual R.
Let's do R minus R and then square that.
No, because that doesn't give you the same thing.
Okay.
Yeah. Is that what?
Is that where the other R from the previous formula went? Is it disappeared because we're squaring the R out and R in?
No, that's actually because we're looking at the problem different in that picture. Like we cut it open and it's totally separate, yeah. Okay, that's the formula I'm about to use, all right? So can you tell me what the outer radius is? Yeah, it's that top edge of, it's the distance from here to the top edge of the washer, right? Which is actually the distance from here to here, but that distance is dictated by what? The f function. Right? So this right here, this distance, this R out, right, in our case,
Yeah.
in this particular case, is just f of x, isn't it?
Yeah. Yeah.
And then the inner radius would be that radius right there, which is dictated by the bottom edge of the rectangle, which is dictated by g, right? So this bottom edge here, which is that bottom edge in here, this is the top edge there, that is our R in, which in this particular example is g of x, right? So we know what R out and what R in is, right? We need to know what the height is. Well, the height is actually the thickness of this, right? And the thickness of this is the thickness of the rectangle, and the thickness of the rectangle has been what for us? dx, right? Right, when we were doing the integrals with the areas, the height was f of x, and then the width was dx. So the width of the rectangle here is the thickness of our washer. So this right here is dx, because this right here is dx, right? Which is this right here, right? That's dx. So the volume of just this one particular sliver, right? This one washer is pi times the outer radius squared. What's the outer radius for us? The f of function, right? So this is the f of x function, that quantity I'm putting in brackets, squared, minus the inner function, which is g of x, that quantity squared, and then times h, but what's h? dx. Sorry that that's over there. That's the volume of one slice. Yes?
I'm sorry to keep asking questions.
Don't then. No, I'm just kidding. I'm kidding. I was just going for reaction then.
I feel like I have a good handle on it. I just want to
Okay.
confirm it. So that pi is only in there because of the formula, and that formula is chosen because of the shape we chose.
That's right.
Okay.
Because in the washer idea, we use that you calculate the area on the top, pi r squared,
Okay.
and then times how deep the cylinder is. Yeah.
But that's true for anything being rotated, though, right? Like pi is always going to be.
Yeah, pi should be here, right? I mean, we should expect it to be here. So that is a generic formula, isn't it? That is a generic formula that will give me the volume of one particular washer. All I would have to do right now is tell you where I am, right? I'd have to give you the X value. If I gave you the X, then you could go and calculate it all, right? You could go figure it out. So if that's the volume of one slice, I want the volume of all the slices, right? I want to add them all up, which means I'm going to bring the integral in now. So the integral, right, is going to add that formula up, and I'm going to start my rectangles where? A, and I'm going to end them at B. So I want to go from A to B. And then just that formula, pi. And wait, isn't pi a constant? So the pi can actually come completely out of the integral. And then I can do f of x, that quantity squared, minus the g of x, that quantity squared, and then all of that dx. Do you see why I put the dx in the back now? Like I put the h here in the formula in the back. I put it there because I knew it was going to be dx, and dx naturally has always appeared at the very end of the integral, so it just makes sense there. If not, then the dx would have been out here, and it just would have looked weird. So I put it in the back. It's all multiplication. Doesn't matter where it is. Yes?
So will we consider like h will like always be dx?
Yes, for what we're doing here. This method that we're using right now, this whole idea of a rectangle wrapped around like this is called the method of washers. Okay? So anytime you have washers, your h is going to be dx. Yeah?
So I hate to ask this, I think I already know the answer, but so this whole picture, like being able to visualize this picture was essential to being able to solve any of these probably, right?
Yeah.
That sucks.
Yeah, you don't need, well, you don't necessarily need to memorize the pictures. Really, at the end of the day, what you need to know is that this is the formula we're going to use.
Okay.
If you have this situation, then this is the formula you're going to use.
Yeah, 'cause I had a real hard time understanding the visualization of how like how you create all these. And
Well, do you see that rectangle is in the x-axis? That's just the same picture exactly,
okay.
right? It's just that rectangle and that axis just written over here so I don't have too much clutter.
Yeah, I see that.
Now, if I ask you to wrap that around the x-axis three-dimensionally, just imagine swinging this through like this, and it comes back around the back side of the board and comes up. I get that washer.
Okay, that's true.
You see that?
There'd be a hole there.
Yeah, that's that picture.
And then on the washer itself, you were able to determine what was like.
So, yeah, so if this swung around, think about that top edge. Swings all the way around, comes back around. That top edge right there, that top edge, the distance from that top edge to the axis of rotation, is actually the same as the height of that function, isn't it? Like that point right there up top is actually the outer radius.
Yeah.
And then the inner radius is the height of that function. Just that right there. That piece right there gets wrapped around, and so that's the height of G.
Okay.
Yeah?
And dx was just the actual.
Thickness of the washer. What's your question?
So for like test purposes like this, like we're not just like gonna use like draw the whole.
Let's do an example. I think we should do an example, a specific example, so you can see the way it should be done.
Well, I know you mentioned on the test, a lot of it's just going to be setting up the integrals rather than
Uh-huh.
actually completing it.
Yeah, we're just going to get them set up, and then we're not going to compute the whole thing, because at that point, we can even use technology to do that part. Yes?
So for that, which you're receiving now,
Yeah.
the area between A and B, like that area shown,
Mm-hmm.
like we have that. We're multiplying that by how it rotates, right? Like,
Well, I'm not sure.
so like when we have, like for the shell
Mhm.
that you showed, like we're like kind of cutting it in half and making it like a prism of some sorts, with one of the faces being kind of like the shape of the one of the cutouts from it, one of our washers.
It's like
An
the,
unrotated washer.
yeah.
Like,
But we're not using the area. The area is not part of it, because our formula, nowhere in our formula do we see the area formula, right? Because this is squared. It's not not truly an area. We're using the pi r squared times h formula, which is the volume of a cylinder. That's the big difference here. We're not finding the area of a rectangle, we're finding the volume of a washer, right? And then we're adding them up.
I was thinking of it like the same way of the cylinder and the prism. Like how you do this when you have like base times width times height. Like another way to think of it is you have like the area of one face and you multiply that by the height. I thought that we were kind of doing that in this one, but
Yeah, it's a little different than that. Yeah. The region between y equals x squared and y equals 4 is rotated about the x-axis. Find the volume of this solid. That's the way the question would be posed. So you're going to start off by just first figuring out what region we're talking about, right? So you've got to draw the curves. And I might have several graphs here, so I'm just going to do a rough sketch. Y equals x squared. Doing this one. And then y equals 4x. Y equals 4x is a straight line, right, with the slope of 4. It's going to hit that parabola eventually, right? Yeah. So y equals 4x. Is it at 4? I mean, I do agree they both do eventually reach 4, but do they reach 4 at the same x value?
Probably not. Yeah.
Oh, you were saying, I thought you meant 4 is the y value.
No.
Oh, you mean,
No.
okay, I'm sorry. I thought you meant 4, I thought you were saying this way. Okay, I apologize, yeah. So 4 at x equals 4, at equals 4. All right, we got it? Everyone see the region? Yes? Okay, I want to take the region bounded by those two curves, which is just this region in here. I'm going to take that region and I want to wrap that around the x-axis. That whole region is getting wrapped. Now, I see when I wrap that if I draw a vertical rectangle in here, right? If I draw a vertical rectangle, like this, then I can see that no matter where that rectangle is, my top function is always the purple, the bottom is always the blue, right? No matter what. So as I move that from left to right. So this is good because that's exactly the general formula I just came up with. We had a function on top, we had a function on bottom, we wrapped that thing around the x-axis. This is like perfectly what we just did. Everyone agree? Okay, so what I'd like to do now is I'm going to signify to you that I'm wrapping it around the x-axis. And I'm going to come over here and I'm actually going to draw this thing again over here. And this is highly recommended that you do this, all right? Again, it's because of where we're going with this. Right now we're wrapping around the x-axis, right? But as you'll see in a little while, it doesn't always have to be the x-axis. It can be a line below the x-axis or above, or it can be vertical lines. So we need to really have a good idea of where everything is positionally. This is my x-axis, okay? I'm wrapping around this. The top function, right, that top function is that line right there, isn't it? That's always going to be the top of that rectangle. And the bottom is the blue parabola. I'm just drawing it curved. It doesn't have to be, like you don't have to draw a line and a curve. It's just the important thing for you to understand here is that the top function, or the top of this rectangle is the purple and the bottom one is the blue. If I wrap that, I get a washer, right? I get a washer. Again, that doesn't have to be a beautiful picture. You just need to know you have a washer, okay? And if I have a washer, what's wrong?
I don't even know how the hell you got a washer. I'm trying to picture in my head. Like, I get it.
I have this. Let me go back to this. Where the hell is it? I got too much shit open here. This one. Let me take out the cylinders. Let me take this function out and let me rotate this back. Okay. Do you see a rectangle right there?
Yeah.
Okay. It's kind of like this rectangle, except this one is moved up a little bit on the bottom. That one's there. If I wrap that around the x-axis,
That little bit of space matters, doesn't it?
well, okay, maybe, but let me wrap it. Let me wrap it. If I wrap that, see it coming around the x-axis?
Yeah.
Do you see it wrapping around?
Yeah.
Coming back to the other side? Do you agree that that's a cylinder?
Yeah.
Okay, now, if I had taken off a little bit of the bottom of that, let's say the rectangle went from here to here instead, then what it would do is it would leave an open space in the middle, wouldn't it?
Yep.
Like that. That's what we have here.
That makes sense.
Okay? You want to see it? All right, now that's not, again, that's not vital that we draw a detailed picture over there. What I think the most important thing is this piece right here. Because I already know that I'm going to be using this formula, pi integral a to b. I have the, what? F of x, that function squared minus the g of x squared, then dx, right? That's kind of my generic formula. Now there's some big little ifs here, or there's a catch to this formula. Our axis of rotation has to be the x-axis for this to work, because that's where we got the formula from. We were wrapping around the x-axis, okay? Really, this f of x was really r out, wasn't it? And this was really r in. Okay, so that's going to matter in a little while. But for this particular problem, I can just use this. My f of x, was that about to be a question or no?
No.
Okay. So my f of x is actually this distance here, right, from there to there. What is that for us? 4x. Right? And then the r in, which is the g of x, right? That's the distance from here to here. That's x squared, right? So again, I will stress again, because of what we got to do in a little while. This is our r out. This is our r in. And then let's just go to this formula right here. Pi, don't forget the pi. Integral. Okay, where does this integral start? 0? And it stops at 4, right? How would we find that this is 4? Either visual inspection, 4 here, you get the same answer, or you set them equal to each other and solve, and you would get 0 and 4 as your two answers. I'm just going to leave that as an exercise for you. That would be 4. And now just f of x squared. Okay, what's f of x squared? 4x, that's squared, right? I'm going to write it as, I'm not even going to square it yet. Minus, and then what's g of x? X squared, then squared. And then whatever that is, dx. So this is the integral from 0 to 4 of 16x squared minus x to the 4th dx. And that right there is relatively simple to do, because antiderivatives of that and stuff are pretty clean, right?
On the exam, would you expect us to also follow through with it?
Not, I would not. I would, at this point, I just want you to set it up. Because it would take us, another couple of minutes to do that, and really that at this point should be almost trivial. Understand? And we got any questions?
So, with the rectangle, like drawing the rectangle, kind of setting that up, is it always going to give you a washer shape?
No.
I think that's
So-
what I was gonna
Right, well, no, okay, let me,
Or does it
this
matter?
is a big thing we're about to find out, and I'm gonna get ahead of ourselves a little bit. Right now, our axis of rotation is horizontal, right? And our rectangle is vertical. So the axis of rotation is perpendicular.
We can make that axis.
Okay, hold on. If that's the case, if you have your axis of rotation is perpendicular to your rectangle, then you will use washers. If it turns out that your axis of rotation is parallel to your rectangles, then we are going to have a different method called shells, which we haven't talked about yet. So you're asking, will it always be washers? It will if your rectangle is perpendicular to your axis of rotation. So today we're just talking washers, all right? We're not going to get into shells yet. Yes?
Can any object be described by some kind of function? Like, could you write a function that would perfectly describe this table and its volume and whatnot?
I think for a simple object like that, yes.
But I mean, for like, theoretically, shouldn't anything,
I'd be hesitant to say anything because, like, let me give you an example. Not of what you're talking about, just an example of something that is counterintuitive. Do you think it's possible to draw a function without picking up your pencil? Okay, so a continuous function that nowhere can you take its derivative. Like if I draw this, right? That's the absolute value function. That's a continuous function. I can draw it without picking up my pencil. The derivative does not exist at that point. But everywhere else the derivative exists. Do you think it's possible to have a function that I can draw without picking up my pencil, but nowhere can you take the derivative? Like the derivative doesn't exist anywhere on that function.
well, it have to have no slope, so
Well, just tell me, do you think that that's possible? To have a nice continuous function I can pick up, draw without picking up my pencil, but if I try and take derivative anywhere, it doesn't exist.
circle.
Well, no, because circle, first of all, isn't a function. So if we just take the top of it, derivative, boom, there, derivative, that exists, right? Okay. So you can sit here and play with it all day. There is an example. Okay? So I'd be hesitant to tell you any function can be represented, you know, or any surface can be represented in the function, because I'd be afraid someone could come up with some weird-ass, you know, object. So I would say there's probably a classification of objects which we can always represent. Okay, yes. I'm going to leave this up here. I'm going to change the problem a little bit. Go ahead.
We're probably going to go over it shortly, but what if it crosses the x-axis multiple times? Like you have a cosine and a sine function.
Oh, okay. Yeah, good question. All right. Let me get to. So the question was just this: what if we have a function like? What if we have a function like this, like the sine function, and we say wrap that around the x-axis, right? Is that what you're talking about?
And then you have like a cosine function also.
Oh, okay.
Kind
Like below it, like this? Like that region between that, wrap around? I don't know.
of, or you should one of them maybe.
Okay, look, we are never going to have a region that will wrap, and as you wrap it, it wraps back upon itself more than one time. That's not going to happen. We're not going to do that, because then you would have a double volume. It wouldn't make sense, right? So we're going to restrict ourselves to that not happening. Okay?
So I was gonna say, so on that last drawing we had, so that rectangle in general, like the top function,
Yeah?
or rather, the bottom function never actually touched the x-axis, but if it did, it would have been a cylinder at that point.
Say it again. The what didn't?
So like the bottom.
Oh, yeah, the bottom didn't. If it had, then it would be a cylinder instead of a washer.
Okay.
Yes, yes. Okay, same exact problem, okay? Same exact problem, but I don't want you to wrap it around the x-axis this time. What I want you to do is to rotate it about y equals -3. That's a different axis of rotation. So I'm going to start with a picture. Okay, I'm going to start with a picture. My picture's going to look almost exactly the same. Well, the graphs are actually exactly the same, aren't they? We have the parabola. We have the line. That's 4x, y equals 4x. This one was y equals x squared. Now, y equals -3 is a horizontal line, right? Y is -3 is a horizontal line that is moved down 3. So it's, if I were to extend my y-axis down like this, if I go down 3, 1, 2, 3, that's -3. My axis of rotation is down here, right? I want to wrap this region around that axis instead of the x-axis. Do we get a different answer?
Yes.
Yeah. Now, if you don't believe we get a different answer, I have a little thing to show you here somewhere. Okay. Look at this is the problem. Oh, you know what? I'm so sorry. I forgot I had this one. Oopsie. I could have done this a long time ago for you. This there's your wrap of your washer. Okay, there. Yes? Yeah. Okay. And then if we do all of them together, we get the solid. Like all the rectangles together give us that solid, right? Okay, what I'd like for you to look at now is all these different scenarios where we wrap around different axes. So this is the same region wrapped around 3 different axes. This one, we're going to wrap it around the x-axis. Here we're going to wrap it around a line that's below the x-axis. And here we're going to wrap this region around a line that's above the x-axis. I'm going to have the computer draw all 3 of those for us, and we're going to see, hopefully it's clear to us, these are completely different shapes, like in terms of their volumes. Theta, washer, region. Let me first do a slice. I should erase all that's on the board. There. There's the rectangle. There's the rectangle wrapped around all 3 different axes, right? This is the rectangle wrapped around the x-axis. You get this nice little washer. But if you wrap that region, that rectangle around an axis that's further down, you've got to go around the whole thing and back up. Now you have a different washer, don't you? And then here, if we wrap around here, we get this shape. All 3 of those washers have different sizes to them, so they have a different volume to them. If I do all of them, all the rectangles possible, I get those 3 shapes, right? And these obviously have different volumes, yes? So the axis of rotation does matter here. All right, let's do this problem. So we've got this, got this.